and references and double references in C and C++. So I prepared two files, scripts, whatever you want to call them, to discuss this. So first off, here is a very simple example C program. And in C, I believe there's a very simple concept of a L value and a non-L value. An L value is a left value, a value that can be put in the left side of an assignment operator. And a non-L value are values that cannot be. And really, I want to distinguish three different types of values. One is just a very primitive value, and that's this guy right here, 0x AB, 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 AB. This is just a literal long. And such values by themselves do not get stored in a register or in memory. And in such instances, this is not an L value. And then a second type would be something like this. This is a value that does get stored for whatever reason. Once I tack on this struct t on top of once I cast this integer value 0x cd 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 into a struct, into the struct I'm defining here, this now is an actual L value you can assign to it, and this is stored somewhere. It's both stored in a register, and I believe it is associated with some memory location. So it can be assigned to, and in fact, it allows us to do that. However, I think this is a weird use case, because true L values are values that are associated, that can be referenced through a variable within your program. And right here, what we see, this value definitely cannot be referenced through a variable. It doesn't have a name. You see what I mean? So this struct t is just holds a single long, and here I'm just creating a static sort of combination literal, but casting it to a struct t, and I will show you that this actually compiles. This is lval.c. So I'm gonna just it compiles. If I don't cast such, these constants that are in curly braces to structs, this will definitely not compile, as we see here. This is another example of something that will not compile, as these are not L values. And even stranger, I know that this is stored in memory because I can reference it. I can attempt to print, print this value. I want to print a long. I'll print it in hex so we can easily recognize it. And I will print the address of A plus 1. This plus 1 will actually increment to the address after A. It will actually increment by 8 bytes in this case. Now this, I want to cast this as a struct t pointer and then this whole thing I want to t's member variable is L, so I want to print out L. Now if I haven't done anything egregiously wrong, this should compile, and it does. Whoa, this is not what I expected. I expected to see the value CD, 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 or rather EF, EF, EF. Huh. The address of A plus 1 T struct pointer. Interesting. The address of A. Don't tell me that. What am I doing wrong here? The address of A does the address of A need to be casted? I don't believe it does. It is a long pointer. When I add 1, give me 1 second here. This shows that I'm not very prepared for this as I should be. We put CD, CD, CD into RAX. RAX. So this value, EF, 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 this value that is an R value but doesn't actually have a variable referencing it, it's being put at negative hex 20 from RBP. And the int I is being put at negative 10 from RBP. Huh. So it almost feels like the compiler is, the address of this is almost, it almost feels like, if I'm not reading it, I'm not an assembly whiz, by the way, but it almost feels like the address is behind it almost feels like it's 16 behind, which is 2 here. It's 16 bytes behind the address of A, lower than the address of A. Wow, wow! I accurately read assembly. So this is definitely stored somewhere in memory. However, I expected, you know, A to be put in memory, and then this guy, which is now equal to EF, 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 this guy without a name. However, for whatever reason, they put this at a smaller address. Oh, I'm such an idiot. That's because the stack actually moves downwards. The stack actually moves downwards. Is that true? The stack starts out at a high value and moves downward. Is that? I wonder if that is true. Wow. Long B. Oops, I did something wrong here. ls. No. So it starts. The stack starts at a very high address, but it definitely, it definitely increases the addresses of these variables. See, it goes from hex 18 to hex 20, which is exactly 8 bytes, which is the size of a long, as we expect. Which means that this is not a this is now at some new location, which, wow, I'm learning something new here. It's putting interesting. So the address of this, the address of A, the address of B is at the address of A plus 8, and I expect the address of this thing, whatever it is, to be the address of B plus 8. But as it turns out, it's above these guys on the stack, which is quite interesting. Rather, it's below in the stack. If you think of the bottom of the stack as address 0, but it's as if this guy was above this line was above long 8. Anyway, that was a kind of a random tangent. So this somehow is an L value in C, and stuff like this, you will never really run into ever. But I want to just highlight this fact right here. So now I'm going to have a function return a struct t, and I'm going to try to assign to its return value. So its return value definitely resides somewhere in memory. It'll be put into registers, and it'll be associated with some memory location. At least I want to say that's the case. However, we can't assign to it. The compiler will not let us. You see, L value required as left operand of assignment. So when the struct is returned from a function, it's not an L value. However, when we cast a literal to a struct, it magically becomes an L value. I just wanted to point it out. I found that quite interesting, as well as the tricks around the as well as the fact that the struct had an address not exactly where I expected it. I mean, it was still around the area. It was all in the same area, but the fact that it wasn't where I expected it was very interesting. So now let's move on to C++. So C++, actually, it defines L values and non-L values in a much more complicated way. But to break it down, it's still very similar. So we have an integer, a regular integer, and this is an integer that now can be referenced through a variable, and it is stored. It's not just a literal; it is stored in register and and in memory. And now C++ introduced this reference type. So an int reference type points to when I assign it to an integer, R and I now have the same, now are referencing the same memory or register, and that's what this magic reference thing does. And when I assign R to 2, I becomes 2, and I'll show that. I did this not too long ago. In fact, just before I started the video. I'll print out the address of both I and R and the values of I and R. I expect these two to be the same and I and R to be both have the value 2. So now we're gonna this is the latest standard, C++ 14. And you see that the addresses are the same and they both have the value 2. Now, one thing that these reference types cannot be assigned to literals. They can only be assigned to L values, which I is one of. So this doesn't compile. And I'll show you that to you right now. You see, the error message doesn't actually mention anything about L values of non-constant reference. I believe that's because so many people use reference types as arguments to functions, and they like to pass a const reference. And I believe because this is so popular, C++, allow this to compile, a const int reference to compile. They allow this to compile, but they do not allow this to compile. I mean, this simply tacking on const changed the behavior of a reference type more than we expected it would. I mean, in C, const just means the value cannot be changed. But here, a const reference type can accept literals, whereas a non-const reference type cannot. It must have an L value. This is an aspect of C++ which I don't quite like. I think it wasn't engineered well. You see, this actually compiles. I'll leave this. I'll leave this T. And then C++, since 2011, C++ introduced a double reference type. A double reference type is can only point to non-L values or something like that. So it cannot point to an L value like I. So here we will see that this line, double reference P, will not compile. You see, it does not compile. It says cannot bind int value to int. It's an interesting error message. But this is precisely what double references are used for. It's used to accept values that are not referenced by a variable. Not quite literals. So int is not a good example here. What we want is an actual object, but yeah, in fact, let me first show you that this compiles. And in fact, let me show you. Let me undo this class right quick. So an int double reference A is equal to int 1. I believe this will compile because this is exactly what double reference is used for. It's used to accept a class that's constructed on the fly. It doesn't have a variable referencing it, as we see it compiles. And this will not compile. Similar to how this line, int reference s equals 1, a literal, will not compile. This line will not compile. Initialize of non-constant reference. Yeah, and guess what? This will compile. I don't like this fact. Yeah, you see it does compile. Anyway, so double reference is used exactly in this instance, and I will show a example where I have this class int. Everything is public, just as for example. Two constructors, one that takes a double reference and one that takes a single reference. And I pass it all sorts of different ints and int references and constant references and int double references. In fact, that's what I do. I pass a literal, an int reference, an int double reference, and an int reference, a constant int reference, and an int double reference. And what's going to happen is this value is the only one that's going to go to the double ref constructor. The rest will go to here. Even the int double reference q. Yeah, because it's hold on, I did not save this file. And as you see, the int double reference constructor is called for the first guy, and everything else calls the constant int reference constructor. Okay. I wonder. Now, here is the final point I want to make about C++ references. As great as references are, or as bad as they are, I believe the true reason C++ introduced the reference type is because of this line right here. Because it enables it, and nothing else actually enables a person to overload the index operator. The index operator is a really tricky operator. First, so the index operator returns an int reference here, and it returns just the value of this class. And so whatever index you try to access, it's associated with just this value of v. So a of 10 is equal to 5. Yes. A of 10 is equal to 5, and I'm going to print the value of a dot, not dot I, but dot b. This is going to print out 5. As we see here. Now, why is I believe the reference operator was spawned for this specific purpose, and every other use, one of a really popular use is const reference types as parameters. It increases efficiency and guarantees that a value is not copied, but it's not changed by the function. These are just things that fell out. The real reason, this is just a conspiracy theory, but the real reason they introduced this reference type is for this reason, to overload the index operator. Because think about what this operator is returning to the user. It's returning the address of v dereferenced. It returns address of v dereferenced. So this evaluates to v. It evaluates to v, but if we were to assign to it, it changes v. So this is exactly what it is. Dereference of address of v. And this whole thing, how do you return this whole thing? that's what exactly what the reference type is. It's the reference type. An int reference is the dereference of an int pointer, and like the compiler will just, when it's passing along the variable, it 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 passes, when it's passing along the variable, it passes it passes it passes the actual address of the variable. So it's passing the same variable, but when it actually uses a variable, it dereferences it. It's that is what this is. Anyway, that's all. Let me apologize if I speak too much gibberish, and speaking is hard sometimes.